Okay, good afternoon everyone, once again. So yesterday morning we started our study of chapter 2, just looking at series. Okay, so sequences were our lists of numbers, one number after another, and we were interested in infinite sequences and the concept of convergence, the way that they might get closer and closer to a limited value. How that concept behaves. We are going to look at series in a similar way. So series are where we're not just listing an infinite sequence of numbers, but where we're accumulating. We're adding them up all the time. Okay? And the notation, we use the capital Greek letter sigma to denote the summation operation. So here's an example of it here at the bottom of page 11. So when you see sigma of xn and the subscript n equals 1 indicates the beginning value of xn, superscript infinity indicates that it's a extended series with no end, it just keeps going on. Okay, this is representing this object here, this infinite summation x1 plus x2 plus x3, etc. So these stand for unending processes of accumulation, and they occur quite all over mathematics. In particular, when you look at numerical methods that are used to solve mathematical models. So these methods, which are implemented with computer algorithms that provide you approximate solutions to given problems, well, there are inherent errors associated with these estimates of solution, and quite often these errors accumulate and you get some kind of an infinite series or an extended series representing the accumulated errors and so on. So they do come up across the board in mathematics. Now, I'll just switch over to the I am going to be following the notes in the booklet, but I am going to present things in maybe a slightly different order. So I'm not just going to work through page by page through the material that it is in the notes. We may hop about to this, okay? But I hope you'll bear with me while I do that. Okay, so to repeat the important, so we saw two important examples yesterday, just to remind you. We saw an example of a convergent series. This is where we added up all the powers of a half, beginning at 1, beginning with the half itself. Okay, so the first value in this series is a half, and then you add a quarter, then you add an eighth. You can view this as kind of tracking the motion of an object starting at 0, but heading towards 1. They take the first step of length a half, then the step of length a quarter, which is a half the remaining distance to 1. They're now at position 3/4, so there's a 1/4 distance left from 1. They step half that distance, an eighth, and so on. The next step will be 1/16th, 1/32nd, etc. So this sum is continually adding on half the remaining distance from 1. So it's going to keep getting bigger and bigger. It's never going to go beyond 1. It only ever adds on half the remaining distance to 1. But it's going to get arbitrarily close to 1. No matter what degree of closeness around 1 you specify, you know what I'm talking about there, I'm talking about epsilon. No matter what degree of closeness to the limit 1 you specify, eventually you will see this sum, after a certain number of terms, creep inside that level of closeness. So it seems reasonable to say that the limit of this infinite series is 1. So attach the value of 1 to this infinite series. Even though naively, adding up an infinite number of things, you can never complete that, of course, if you think of it as some kind of mechanical process or some kind of process happening in time. It takes some minimal amount of time to add a term to the series. You're never going to complete adding up an infinite number. But nevertheless, it seems reasonable to attach the value of 1 to that. We also saw a divergent example. And our divergent example was what we called the harmonic series. So here, again, we're adding smaller and smaller fractions, but they're not getting small as fast as the powers of the half get small. We're just adding up the reciprocal of every positive integer, 1 plus a half plus a third plus a quarter. Okay, and yesterday we saw a grouping argument. So we were able to group these terms together in such a way that we always could achieve something bigger than a half. You take a third and a quarter, you add those two together, that gives you something slightly larger than a half. Take the next 4 terms after that, the 5th, the 6th, the 7th, and 8th. They add together to give something slightly larger than a half. Then you take the next 8 terms, the next 16 terms, the next 32 terms. We were able to show that you keep on accumulating terms which are bigger than a half. Okay. So we saw a grouping argument which persuaded us that this series grew without, this series grows without any overlap. So whatever huge number you throw at me, if we wait around long enough, eventually we will see this series get above that value. Now we may have to wait for an awfully long time. This series increases very slowly. It increases at roughly the speed of the logarithm function. The logarithm function increases very slowly, just as the exponential function increases very fast. The logarithm, because it's the inverse function to it, increases very slowly. And we had our nice example of stacking bricks, which hypothetically, stacking bricks simply on top of each other, edging each one out a little bit, theoretically could achieve any overhang whatsoever. You know, the stack of bricks starting here, and the top one could end up as far as we want away from the base of the starting brick. But we did a quick rough calculation that said to achieve an overhang of about 3 meters, with the space across the desk here, we needed some crazily high stack of blocks, okay? Many times the diameter of the observable features. Okay? That's just gives you a flavor of how slowly this series is increasing. But it is increasing without any effect. Any questions just about those 2 examples before we move on? This harmonic series in particular is a very important example to keep in mind a lot of the time. Okay, so I'll often refer back to it. Okay then, so we need a good definition of convergence. Okay, we've already seen a careful, rigorous, formal definition of convergence for sequences. We're going to make use of that to define convergence for series. Okay? Really, convergence for series is really just an example of convergence for sequences in the way that we're going to see now. Okay? So first we have the concept of a partial sum. So for an infinite series, so speaking in general now, for an infinite series like this, which is the sum of an infinite number of terms, we define the partial sum, take partial sum. Okay, so I'm repeating what I did yesterday morning here, but there's no harm. The take partial sum, which we might call SK, we define this as SK. You're just adding up the first k terms. So it's x1 plus x2 all the way up to xk. Okay, so it's not this weird kind of infinite series, it's just adding up the first k terms. So no conceptual problems about what sk is. Adding up the first k in this from the infinite series. And if the sequence of partial sums so the sequence of partial sums is this sequence of quantities sk, as k goes from 1 to infinity. If that sequence is convergent, then we say the series is convergent. If this sequence of partial sums is convergent, so is the series. And we say that sum of the infinite series equal to the limit k goes to infinity of the partials. So that's a very nice idea. It seems entirely reasonable. The value we attach to the infinite series is the limiting value that we observe for the sequence of partial sums. We form the sequence of intermediate finite sums. We watch the evolution of that value. If that is converging and settling down to a limiting value, then we say, yes, the infinite series is convergent, and whatever this limiting value is, that's the value that we say the sum is the infinite. Okay. So that is the definition, more or less, in definition 2.3. Page 12. And queries just about the definition. Okay. Now, so it's not like a whole new concept of convergence. Really, it's just convergence for sequences, where we're talking about a sequence of partial sums. Now, an observation that we made yesterday, and I'll repeat it now briefly, was that this convergent series we looked at the top, the half plus a quarter plus an eighth and so on, intuitively, the reason that is convergent and it's converging to 1, it's a series of positive steps, but the reason it's converging is because the steps are getting very, very small, very, very fast. Step size is shrinking, disappearing away, converging to 0. There are always positive, increasing positive steps to take, but the size of those steps is getting very, very tiny, very, very quickly. And that's what allows the infinite series to converge. And it seems that that is necessary. If you've got any kind of infinite series where the step size is not getting smaller and smaller and converging to 0, surely that will prevent the series from converging. Okay? Because you'll be taking steps that are not converging to 0. So every so often there'll be a kind of a large step which will move the partial sum a significant amount and stop it settling down to a limiting value. That's the first observation, but then immediately we saw the harmonic series, which says that the implication does not go the other way. Just because you've got an infinite series where the step size is getting smaller and smaller and disappearing away, converging to 0, that does not guarantee that the infinite series converges. Okay? Because here's an infinite series, the harmonic series. Step size there is converging to 0. These are positive steps that are getting disappearingly small. But there's still enough weight in them. There's still enough accumulation going on that can grow this series larger than any specified value. You can accumulate enough of those terms. And there's an infinite number, an infinite series. So we get the idea from these examples that if the series is convergent, it must be that the step size is convergent to 0. The terms of the series is converging to 0. However, the harmonic series shows that the opposite is not the case. Just because the step size converges to 0 does not mean that the series has to converge. Okay. So this goes by a name. This is called the general term test. And it gives us our first way of recognizing, well, we can't use it to recognize convergent series, but we can use it to recognize divergent series. If we do ever see a series where the step size is not convergent to 0, we will know that it is not a convergent series. So if we look at the statement of the general term test on page 14, you can state it in two different ways. You either say if the limit of terms an is non-zero, then that means the associated infinite series is divergent, that it diverges. Or you can say it the other way around. If the series converges, that implies that the limit of the terms is 0. And that's the way around that we're going to prove it. So we're going to be able to prove this second version of the statement. Okay? we'll be able to prove it using our definition of convergence in terms of partial sum. That's just one, two. So we will prove that if the sum from, I may as well use the notation there, if the sum from m equals 1 to infinity of am is convergent, then the limit of the terms is 0. Okay, we have this intuitive idea that it has to be. The step size wasn't disappearing, the infinite series couldn't converge. But we can prove it here. Now, a bit of a diagram helps. So we let S be the limit k goes to infinity of the partial sums, Sk. So let Sk denote the partial sum, k partial sum. K partial sum of this infinite series. We let capital S be the limit of that, okay, because we know that we're assuming that the series is convergent. Well, if I know my partial sums are converging to S, I know that eventually partial sums have to be within any given distance of S. Okay? So that's useful. I can specify any size of interval around S, and eventually there will come a point after which all of these partial sums, all of the SKs, have to live inside this interval. Okay? The SKs are converging to the limit S. So the definition of convergence for sequences says eventually they all have to live within whatever size of interval one cares to specify around the limit S. Now, if we let epsilon greater than 0 be given, what we are trying to achieve, we're trying to prove that the limit of am is 0. So we're trying, I'm going to leave a big gap here enough to argue it. We want to show that for all values of m greater than or equal to something, the absolute value of am will be strictly less than epsilon. Okay, remember, the definition of convergence for a sequence, we're trying to prove that the sequence of terms am is convergent to 0. The definition of convergence says, given any positive value of epsilon, eventually, so for every value of the index little m after some point, the absolute values of the AMs have to be smaller than epsilon. Okay? They have to be within a distance epsilon of 0. And normally we see inside this absolute value, we see the absolute value of AM minus the limit. But the limit we're talking about is 0, so that's why I thought I'd simplify to just the absolute value of AM. Trying to show that that is less than epsilon. And the task here is to find the number that goes here. How do I know that such a point in the sequence of terms exists? Well, what this point is somehow going to come from the fact that the sequence of partial sums converges. And we notice that there's a nice way that we can express a term of the sequence in terms of the partial sums. If you think of the partial sum Sk, if you subtract the partial sum that came before it, then you get the term A sub k. Remember, what is Sk? Sk is just the sum of the first k terms. A1 plus A2 plus A3 plus A4, etc., all the way up to AK. Sk minus 1 is the sum of the first k minus 1 terms. A1 plus A2 plus A3 plus A4, all the way up as far as AK minus 1. So all of the terms in this partial sum are in this partial sum, but there's just one extra one, that's k, and that's AK itself. Okay? So to understand that, go back to the definition of the partial sum, just the sum of the first k things. So if we subtracted Sk minus 1 from that, the only thing left remaining would be the the one at the end. Okay. In our case here, that's the number 8k. So this quantity 8k, which I'm trying to make as small as possible, it's equal to the difference between consecutive partial sums. Well, that's quite helpful. Because remember, the partial sums are convergent to S. And I know if I wait around long enough, eventually all the partial sums get trapped inside this interval. But if all the partial sums are trapped inside this interval, the furthest distance apart the two of them can get is the diameter of this interval. If my sk and my sk minus 1 are trapped inside this interval, the furthest apart it can get is just the diameter of the interval, the total distance from one end to the other. But I'm trying to keep this small. I'm trying to make that smaller than epsilon. So that tells me that the appropriate radius I should choose is epsilon over 2. Okay, the value of epsilon has been given to me. So I want to talk about this interval around S of radius epsilon over 2. So since Sk converges to S, k goes to infinity, there exists a point, capital K, I'll call it, such that for all values of the index little k bigger than capital K, the absolute value of Sk minus the limit S is less than epsilon over 2. Okay, that's true. I know the capital K exists because I know the sequence of partial sums is convergent to S. I've chosen strategically the radius of epsilon over 2 to use. Remember, I'm trying to control the size of AK, of the term of the original series. So if I can control the diameter of that interval, and I know that that diameter is equal to epsilon, then I know that the values of these terms, AK, will be less than epsilon. And now, if I choose, if m is greater than or equal to k plus 1, if m is greater than or equal to k plus 1, then the absolute value of am, which by definition is equal to the absolute value of Sm minus Sm minus 1, the difference between two consecutive partial sums. But then I just measure this distance via S. Now this looks a bit odd, but what I've done there is I've added S and subtracted it. I've added in a minus S and a plus S. So I haven't changed the quantity inside the absolute values. I've just subtracted S and added S, minus S. So I haven't changed that value. This is still an equal sign. But now I can use the triangle inequality to split this absolute value up as the sum of these two absolute values. And I know that both of those are less than epsilon over 2. Which is equal to epsilon. Epsilon over 2 is epsilon over 2. So what's going on here? I'm saying if m is greater than k plus 1, the two partial sums, Sm and Sm minus 1, are both trapped inside this thing. Okay, so the furthest apart they can get is epsilon, which is the diameter of that. So have I succeeded? Have I found a value here after which am has absolute value strictly less than epsilon? Yeah, this value is k plus 1. Well, that's the correct value to go with. I know capital K plus 1 exists because I know the capital K exists with the necessary property about what's going on with the partial sums, because I know the partial sums are convergent towards X. So this, seeing the definition of convergence for sequences being used again like this should help you to understand it and appreciate its power. How it enables us to prove these results that we get an intuitive idea of from looking at some examples. This intuitive idea that if the series is convergent, the step size has to be disappearing and convergent to zero. So this proves that the AMs are convergent to zero as required. To check if I prove that, you just look at the necessary parts. Epsilon greater than zero is given here, and here we get the existence of some point after which the AMs have absolute value less than epsilon. So they're within the distance epsilon is zero. And that can be done for any value of epsilon whatsoever. So the AMs are getting arbitrarily close to zero, i.e. they're convergent to zero. So that's the proof of our general term test. So now if we ever observe a series, an infinite series xn, as you're walking down the street, if you ever see a series, the sum of all xn, and it's not the case that the xn's are converging to zero as n goes to infinity, what do you know? You know that the series is not convergent. Okay? Because we've just proved if the series is convergent, the terms have to converge to zero. So if we spot the series whose terms are not convergent to zero, then we know that the associated series is divergent. So this is a tool, this general term test is a tool which can allow you to detect divergent series. It doesn't help you detect convergent series, right? Because the harmonic series, remember, is our example that it doesn't work the other way. Just because you see a series whose terms are getting smaller and smaller and converging to zero, that does not mean that that series converges. The harmonic series acts like that. Still, even in those vanishingly small steps, there's still enough weight in them to make the harmonic series diverge, albeit extremely slowly. Okay. Any questions about that? Yes.
When you kind of eliminate x and give like minus it and then made it plus again to cancel, in the next line, why go minus the x's?
Well, because, so what that's an example of, if I have the absolute value of the difference of two quantities, I know that that's going to be less than or equal to the absolute value of x plus the absolute value of y. So it's an example of the triangle inequality. I mean, what I'm kind of saying is that here's the limit s of the partial sums. My Sn will be floating around here somewhere. Sn minus 1 might be floating around here maybe. And what I'm saying is that the distance between these two is less than the distance from Sn to S plus the distance from Sn minus 1 to S. See, what's the maximum that the sum of those two distances can get? The maximum that the sum of those two distances can get is if they're both at either end. So it's the full diameter of the interval. That's the worst that it can get. That's the largest that that distance can get. But I'm still safe because I've arranged it so that the interval has radius epsilon over 2, so the diameter is only epsilon. So even if it's the worst it can possibly be, this absolute value of an will still be less than that given value of epsilon. Does that answer the question? Yeah. Any other queries at all? Okay, good. So please study that result. It will repay study. and it's a good example of using the definition of convergence for sequences and getting some more out of it. Now we've suddenly got a new result about series and a useful tool for detecting divergence. Okay. For our next trip, or not trip, for our next examination, we're going to make things a bit more concrete. And we're going to look at a particular family of series. Okay, so that previous proof was what we call very general. We were talking about any kind of convergent series at all. Now we're going to make it a bit more particular, and we're going to look at geometric series. A geometric series is one of the form okay, so it's an infinite series of terms xn, where the xn has this form here. So it has a particular form. The term xn is equal to some quantity a times another quantity r. The r is raised to the power of n minus 1. Where a and r are fixed parameters. So this series, they're called geometric series. Geometric kind of suggests the idea of multiplication. These series proceed by, they generate each term as some fixed multiple, here is r, some fixed multiple of the previous term. This is the kind of pattern that a geometric series has some initial term a, and after that each next term is obtained by this fixed multiple r of the previous term. Okay? So a is the initial term. A is the initial term, and r is a common ratio of consecutive terms, sometimes called. You take two consecutive terms, one term after another, and you divide one by the other, you put them in a ratio, you always get the quantity r. Okay. Divide one term by the one that came before it, you always get r. So an example is that example we looked at, which was all the powers of a half. This is geometric, and this has initial term and 1/2, and common ratio also 1/2 as well. So that very first example of convergent series was one we looked at. Now what we'd like to do now is to completely describe the convergence and divergence behavior of such series. Just give a complete description of when they're converging, when they're diverging, and it's very complete for when they are converging. We're going to be able to say exactly what value they have. So this is all bundled up in Theorem 2.4, which is called the geometric series test. Theorem 2.4 gives a complete description of their convergence behavior. Well, we'll begin by looking at an extremely simple case. What if the initial term happened to be 0? If the initial term happened to be 0, then the whole series would just be a big long line of zeros added together. And there's nothing much interesting going on here. That's what we call trivially convergent. Not incredibly interesting. Won't win any prizes for saying 0 plus 0 plus 0 plus 0 is 0. Okay? It's a trivial case. This is what we call trivially convergent. So we'll assume, for the rest of the time, we'll assume that A is non-zero. We've dealt with the case where A is 0, now we'll assume that A is non-zero. I'm not running out of time here. If R is equal to 1, then the series also has a kind of particularly easy form. It's just going to be A plus A plus A plus just adding A up an infinite number of times. And if A is non-zero, this is also a bit trivial and uninteresting, but this time it's trivially divergent. Okay, you've got some fixed non-zero quantity A, you're just adding it up an infinite number of times. That's going to grow and grow and grow without any upper limit. Okay. So this is trivially in a sense, those aren't the interesting cases to look at. Otherwise, we need a nice way. We need a nice way to think about the partial sums. Think about its partial sums. Remember, the k partial sum of the series is adding up the first k terms. Well, if we look at Sk for this geometric series, A plus AR plus AR squared, all the way up as far as AR to the k minus 2, and then the last term is AR to the k minus 1. Remember the pattern is A times R to the n minus 1. So here is the k partial sum, the first k terms. Now this has quite a bit of, there's a very strong pattern here that each term is R times the previous term. And we can exploit that if we consider the quantity R times Sk. The first term of this will be AR, but I'm going to write it down here instead. The second term will be AR squared. AR k minus 2, we get AR k minus 1, and we get one term poking out at the end, which is A times R raised to the power k. Okay. We've multiplied all those terms by R, we've got to shift them over one click to the left. And then what I'll do is I'll subtract one from the other. I'll do Sk minus R times Sk. Well, everything cancels, you see. So everything is the same as everything else, so it all cancels out except for this first bit here, A, and this last bit here, which is minus AR to the K. Okay. You can see that. You just simply subtract one line from the other. Almost everything cancels, except for the first A and the last negative A times R to the power K. Well, this equation now gives us a very nice formula for Sk, which is this quantity A times 1 minus R to the power K all over 1 minus R. Agreed? You factorize the left-hand side as 1 minus R times Sk. Factorize the right-hand side as A times 1 minus R to the power K, and divide across. So from this, we see that if the absolute value of R is strictly bigger than 1, what's going to happen to the partial sum? As k goes to infinity, as k gets larger and larger, if the absolute value of R is bigger than 1, what happens to R to the k? It shrink or grow? Grows. If R is a number bigger than 1 and you multiply it by itself, it gets a little bit bigger. And it gets bigger and bigger each time you multiply it by itself. So if the absolute value of R is bigger than 1, then Sk is divergent. Sk is a divergent sequence. And so the associated series, the associated geometric series, is also divergent. Really, here we're using the algebra of limits theorem for sequences, because we got a whole bunch of constants there, a, 1, r, but then we got r to the power k, a sequence in there, which is divergent. So, well, that's bad in the sense that it's divergent, but it's good, the fact that we can recognize it and tell that it's divergent. On the other hand, if the absolute value of r is strictly less than 1, then what's happening to r to the k? Start off with something which is absolute value less than 1, you square it, it gets a bit smaller. And you cube it, it gets smaller still in absolute value. So if the absolute value of r is strictly less than 1, as you raise it to the power k, you're going to get something that converges to 0 as k goes to infinity. So again, using the algebra of limits theorem for sequences, here I have sk built up out of constants and a sequence here, r to the power k. But if r to the k is going to 0, then sk will be a convergent sequence. So now, sk is convergent. And we can go one better, we can say exactly what its limit is. It's equal to the limit of all of this as k goes to infinity. Well, the rk bit goes to 0, so it's simply a over 1 minus r. And this, of course, is the sum of the infinite geometric series as well. Notice there's no problem with dividing by 1 minus r, because all the way up at the top we dealt with the case if r was 1. So we dealt with that already, so we're assuming that r is not 1 in all of this step. We've already talked about the case r equals 1, so this is all taking place under the assumption that r is not equal to 1. There's one more case I haven't mentioned, which I've left out. Anybody spot what it is? I dealt with 0a, then everything else was non-zero a, so I dealt with all the a's. Sorry, suggestion? Yeah, but which value of r have I not dealt with? Negative 1. Negative 1. Look, I dealt with the case r equals 1. I dealt with the case absolute value of r strictly greater than 1, absolute value of r strictly less than 1. But I've dealt with r equals 1, so the only case I haven't mentioned is, I probably could have mentioned it along the way more efficiently, but last case, the last remaining case is a non-zero a and r equal to minus 1. But then what does the sequence look like? It looks like this. Add a, subtract a, add a, subtract a, add a, subtract a. Is that convergent or divergent? My finger settling down to a limiting value? No. Well, remember we defined divergent was not convergent. If you're continually stepping back and forwards by a fixed amount a, you're not convergent, so you're divergent. It's not exploding in value, yeah. Normally we think of divergent, we tend to think of that normally as it's getting larger and larger. Okay, it's not getting larger and larger, but it's not settling down to a limiting value. But clearly divergent. So that's a complete description of geometric series. We've been able to say exactly when they diverge, exactly when they converge, and when they do converge, we've got the ultimate result, which is an actual formula for the sum. But these are very hard to come by for infinite series in general. Generally, we won't be able to obtain a nice formula for the sum. In general, all we'll be able to obtain is just a decision about whether it is converging or diverging. Okay, so for your tutorials this week, I think questions 1 to 6 on the first tutorial sheet are available. Just give me one last 10 seconds. Some of those questions I've just dealt with, questions 2, 3, and 4, we've really been talking about here in this lecture. Ask questions of your tutors about those if you need further clarification. But otherwise, questions 1, 5, and 6. And we'll continue with this next time, okay?